Start recording. All right. So we had a problem with the filming last time. It crashed halfway through. So today we're talking about ECE260 Lab workflow. And this is what you're expected to do every time you come to lab. Every new lab is going to follow the same workflow, although the problem is going to be different. So one is create a logical schematic. And most of our coursework will go towards how to get to step one. Lab starts after this. Okay? Your lab work starts after you've created a schematic. Step two is assign chips. Step three is assign gates. 4 is previs schematic. 5 is previs breadboard. 6, build the damn thing. 7 is test. At which point, test produces an iterative process where you go back. If it doesn't work, you may have to go back to create the logical schematic again. Usually, it'll be maybe there-ish, okay? But sometimes you do have to go all the way back. So, in order to go through this workflow, I'm going to start with a given schematic, and we're going to build it. You guys don't know anything about logical gates yet. We haven't dealt with it. We barely know how to count. But we can build something because it's effectively putting together puzzle pieces. So I'm going to give you a schematic. Right? And this is a schematic made up of gates or devices and wires. So the weird looking D thing is what's called a NAND gate, and everything else is a wire. Where I have put those bold dots, those are junctions, meaning that the wire is connected together. So I've got 2 inputs, X and Y, and I've got some output, call it F. Now each one of these is a NAND gate. Specifically, it's a 2-input NAND gate. From this, we have enough information to go and start building up a device. Okay? First off, we need to get ICs. Integrated circuits have some number of chips on them, or some number of gates on them. Open board camera. So ignore all that for a moment. That is a chip. And if I can get this to counterbalance well, and then also focus. There we go. This is a, where is it? Oh, it's still not focused. This is a 74LS00. I promise you that's what it says. I did get this to focus before, right? Well, all right. The pertinent features of this chip. Oh, you've almost got this. You can do it. Damn you. Technical difficulties here. I don't think I'm going to get it. All right, that's actually not too bad. There we go. That's not too bad. It's got pins along two sides of this package. It's called a dual inline plastic package. It's DIP for short. And this is a 7400, which is a quad 2-input NAND gate. So the chip itself has a pinout. It has a total of 14 pins. 1, 2, 3, 4, 5, 6, 7. Has a total of that many pins, 14 pins. There is some kind of pin 1 marker on every chip. It might be a little notch taken out of the top, or it might be a little dot, or it might be both. Regardless, if you orient that notch so that it is at the top, pin 1 will be on the top left. And then you count down pin 2, 3, 4, 5, 6, 7. And then this is where some people make mistakes. 8 is directly opposite of 7. And then the pins count up. 9, 10, 11, 12, 13, and 14. To find out how this pin is internally connected, you should consult the data sheet. The data sheet, mouse. All of these are available on the M drive. Raise your hand if you don't know what the M drive is. Okay, the M drive, if you log into any of the lab machines, is the class directory. It's the ECE class directory. So there's a folder inside the M drive called ECE260. There's also one for ECE201 and 160 and all these other courses. Inside, it's all the relevant files that I want to give to you. So the syllabus is on there. What else? The sample lab format, leave all that, don't touch that. Not like just not something you need. But among them is data sheets. So the data sheet for the 7400 is right here. And of course now, who knows where it went? I've got to get to desktop. It didn't work so well there. Nope. All right, let's do it this way then. Open board, add in a window. Yeah, okay, there's my data sheet. Sorry, that took a second to get popped up. This is the data sheet up in the top right. It says what the part number is, a short description. What we really care about here is the pinout. And all by itself, it doesn't seem that helpful. Okay, but I'm going to copy it over and I'll show you what's happening internally. So it is 14 pins. I'm going to copy this over. We've got 1A, 1B, 1Y, 2A, 2B, 2Y. This one is called GND. 8 is 3Y, 3B, no, 3A, 3B, 4Y, 4A, 4B, and finally VCC. Okay. Internally, there's a lot going on. It's pretty simple to see, actually, once I draw it out. Each of these groupings that starts with the same number is all part of the same gate. There we go. So there are a total of 4 gates. It's a quad 2-input NAND. So there are 4 NAND gates inside of this. We don't know what a NAND gate does. Doesn't matter for our purposes. There are 4 of them. Y is always... Oh, you can't see. Darn it. Next time, just yell at me, Rob. Don't let me keep on going. Okay. So there are 4 of them. Y is always the output, and then A and B are inputs. Y is the output, A and B is the input. The only two pins left that aren't part of one of the gates are VCC and ground. Ground really just stands for a connection to a common reference voltage, 0 volts. VCC, which used to stand for collector voltage, is usually just connected up to positive 5 volts. So with that said, we can take this circuit, through the magic of computers, take that whole thing, make it a group, copy and paste it to a new page here. Oh, jumped ahead of ourselves. We can take this and we can annotate this with pin numbers. And that's part of our list. We want to assign, well, assigning chips, there's only one chip for this particular example. Assigning gates is the next step, and that's what we're doing here. We have these 4 NAND gates, and we've got a chip with 4 NAND gates. All right, and they're numbered 1, 2, 3, and 4. So how do we want to assign them? Well, there's lots of different ways we could assign them, but for today, some ways are better than others in terms of how we're going to wire things. But for today, I'm just going to wire them in order. 1, 2, 3, 4. Now, after we've assigned them, now we know every single pin connection that needs to be made. Because I know that pins 1, 2, and 3 are associated with gate 1, and 4, 5, and 6 are associated with 2, 8, 9, and 10 are associated with 3, 11, 12, and 13 are associated with 4. And I've left a little bit of a space because those ones that are off by their lonesome, those are the outputs. So I'm now going to annotate pin numbers. This is all part of the process. So that's 1 and 2, that's 3. This is 4 and 5, and that's 6. 3, the inputs are going to be 9 and 10, and the output is going to be 8. And finally, gate 4, the output is 11, 12, and 13 are the inputs. At this point, we might have decided to start wiring, but the steps that I want you guys to go through are as follows. Now that we've assigned gates, we've got a pin-out schematic, I want to go through some pre-visualization. It's going to make wiring up your circuits easier. All right, and to do that, we're going to use a tool called fritzing. Fritzing is a nonsense made-up word, but it is a schematic capture package. You put a schematic in, and you can easily create breadboard layouts with it. Okay. To do fritzing, start a new sketch here, or crash the computer, one or the other. Okay, come back over here, go to fritzing. Okay, this is the wrong fritzing window, untitled. So when you start fritzing, save. That's as big as I can make it. When you start fritzing, there are a couple of tabs along the top. One of them is the breadboard view. Now raise your hand if you've never used a breadboard before. Okay, about half of you. A breadboard is a tool for prototype design. That's sort of over there. I've got a breadboard right here. You'll notice it looks pretty much the same as what's on my screen in fritzing. The nice thing about a breadboard is you can take hookup wire, 22 gauge wire, and you can connect it up just by sticking it into one of those holes, and then you stick it somewhere else, and that makes a firm electrical connection, firm-ish. Okay, there are limits to what it can do. But it's arranged into two basic parts, the center part and the exterior parts. The exterior parts are these red and blue lines. Those are called power rails, okay? And if I click on one of these holes, it's going to show me everything in fritzing that is electrically connected to it. So there it is. All of these holes that are near the blue line, and you can see them on here, all of those holes are connected in parallel to one another. And the red lines are also connected in parallel, but not to each other. And also not across the edges of the board. So this bus down here is different from that bus down there. Now the first thing we're going to do when we wire up a circuit board, usually in this course, is we're going to hook those up together. We're going to take power and run it across the power. We're going to take ground. We're going to hook it up to ground. Now what that does for us is it connects both of the blue lines, blue rails, and both of the red rails. These wires stay in my breadboard all semester long, except for the first class where I forget to put them in and cause an error. If you were here last hour, you would have known, but you don't get to see that fun joke. The interior is a little different. It's split right down the middle. That split is designed to perfectly fit a single dip package across it. And unlike the power rails, which go horizontally in this case, the interior rails go vertically. So there's only 5 tie points. Every one of these holes is called a tie point, T-I-E. So if I put a chip here, there are 4 wires that connect to that pin of the chip, or 4 tie points that connect. So if I wanted to hook up that chip to something, I could stick one wire right in that, and then another wire on the other side. And aside from the fact that this wire is ridiculously long, much too long to be used, now these 2 wires, these 2 pins on this chip are connected. Okay, so the first step in the previs process is a previs schematic. So I've shown you the breadboard tab. The schematic tab is much more boring. There's literally nothing there. One of the first things I'm going to do is use the search function because I need to have a couple of helper devices. One of those things is I need a power source. Okay. The next thing I'm going to look for is a 7400. And in this case, I found it because I just did the demo an hour ago. But chances are you don't have it in your version of fritzing. What you're going to have to do is go to the M drive, and in the lab folder there is a file. And if I can, external, no shift, internal, nope, external, nope, not going to work for me. Fritzing Lab Demo. You're going to just be able to click and drag it. When it comes time to deal with that, I will show you how to do it. But once you do, you get a whole bin of parts. Can you see that right side there? Yes, you can. A whole bin of parts. There are many different bins. My bin is called the ECE260 bin. And so we're going to get a couple of things out of that. First off, we are going to get a 7400. This should look familiar from the data sheet. It's 1A, 1B, 1Y, and so on and so forth. We're also going to get a few helper items. One of them is a set of switches. These are going to be stand-ins for our test apparatus inputs. And we're going to get some logic indicators. Those are going to be stand-ins for our test logic outputs. At this point, we've got almost everything we need. I need just a few more pieces out of the core components here. Specifically, I'm going to grab a ground symbol, a VCC symbol or a 5-volt symbol, and then I'm going to grab something that's going to make my life a lot easier, and it's called a net label. Net labels are logical connections. So if I have a few of these net labels, just like in the breadboard, when I clicked on something, it showed me everything that it was electrically connected to. When I click on a net label, all of the net labels that have the same name show up as connected. So I'm going to call this guy X, because that's the name of one of my inputs. Call this guy X. Call this guy X. Okay. And I'm going to need a few of these, because every place I want to use X, I'm going to put one of these net labels. Put another net label in here for Y, and one more net label in here for F, the output F. Okay. Now, I'm going to hook these net labels up to things first. So the first thing I'm going to do is I'm going to use my cadet switches as my temporary input. So I'm going to connect up the X input to a switch. I'm going to connect up the Y input to a switch. I'm just rotating it with Control R just to make it look right. I'm going to connect up the output F to the LEDs. So now again, if I click on X, only the ones that are labeled X are highlighted. When I click on Y, there are no other net labels named Y, so nothing lights up. When I click on F, only F lights up. Okay. So now, with that done, I don't really need to look at the cadet switches or the cadet lights anymore. I'm just going to take these, move them out of the way so we can focus on wiring up the chip itself. The power source, VCC and ground, I do have to make sure that I have common grounds. Okay. This is, again, more as a pre-visualization tool. I'm going to take that 5-volt and ground net label, and I'm going to hook them up to VCC, or I'll take the whole chip. To actually make a wire connection, I just hover over it. It'll turn blue. When I click on it, it turns yellow. Notice that the 5 volts in the corner has turned yellow as well. Click and drag it. Same thing there. Okay, so now I need to have my schematic open at the same time. So here's, he said put that down there, huh? Or move up. So I've got my fritzing schematic open. Also now I have the schematic that I want to create. So I'm just going to go ahead and build that. So let's start at the left side of that schematic and work our way to the right. So starting at pin 1, pin 1 is connected to X. So I'm just going to put that net label there and throw it in. Pin 2 is connected to Y, which oddly enough, I don't see any other Ys. So I'm going to copy and paste him. Okay. Pin 2 is connected to Y. Pin 3 is connected to 2 different places. So I need to be a little careful with how I draw this. One of them is connected to 5. So there it is, 3 to 5. And unfortunately, that also looks like it's now connected to pin 4. So I'm going to have to introduce some bends into this wire. I can just click anywhere on the wire and introduce some bends like that. What is pin 4 connected to according to the schematic? The worst you can do is be wrong, and then I'll laugh at you or I'll be mean-spirited. But you're all adults, you can handle it. It's connected to X, yeah. So again, rather than doing something like this, which is going to cause wires to start crossing, I'm just going to make use of these net labels. Okay. 5 is connected to 3. We did that. 3 is also connected to 9. So I'm going to do something like this. Try to keep it so that it's not hiding any information from me. So I'll be generous. I'll go really far and around. What about pin 6? Where does 6 go? Somebody on this side of the room. 6 does not go to F. 6 goes to 12. So again, I have to do the first connection, and then I've got to be a little bit nicer about it here, like so. Yeah, not the most optimal schematic, but we'll live with it for now. 7 is ground. We've already connected that. 8, where does 8 connect to? 13. Okay. And again, it's causing some confusion here. We've got some wires crossing. I'm not a huge fan, but maybe we can fix this in a little bit. What else do we have? 9, we've connected up to 3 and to 5. And I can check that too. Just by clicking on 9, I see that electrically it's connected to 3 and 5. So I've made that wire connection. 10, what's 10 supposed to connect to? 10 is right there. It connects up to Y. So I'll grab another Y connector. So there's Y, and I'll drag it in. And now, yeah, I'm going to be even more generous with this. Take this all the way out so that Y doesn't get crossed over. 11. 11 isn't, I don't even see 11 on my schematic. Where's 11? Yeah, you can see that right now. 11 is F. So rather than trying to make a wire connection all the way to these cadet lights, I'm just going to take this net label and connect him up. All right, now there are a few things I can do to clean this up. All right. What I'm trying to do most often is avoid wire overlaps. All right. Now, it would be perfectly permissible to swap gate 3 and gate 4 and rewire this, and that might result in less wire overlaps. But just due to time constraints, I'm going to leave it as is. I'm going to implement it how we've drawn it. You should go through a couple of permutations and see if you can make it a little bit cleaner. Because a little bit of work put in beforehand is going to simplify your life in lab much more. So you may ask yourself, why did we draw this schematic when we had a perfectly serviceable schematic over here? The reason is a term called forward annotation. Forward annotation means whatever you put here in this schematic, the breadboard will remember it. So see all these dashed lines that have appeared? Those are indicators to you, the designer, that, hey, in your schematic, you said that these two things were connected, so you should probably, put a wire there. Because most of my CAD packages are smarmy and snarky like that. Okay, so we've got a few things going on here, and we're going to arrange them so that they're a little bit nicer. These cadet lights are going to take the place of some of my instrumentation, as are these switches, as are these batteries. Okay, and what I'm going to do is I'm going to move them off to the left side of the board. Then I'm going to take this chip, and I'm going to leave myself a little space. I want you to look right now. Do you see how on the bottom, let me see if I zoom in. Right now, all the pins on the chip are red. Everybody see that? That means that none of these are connected to anything. When I stick them on the breadboard, notice the top row is blue, but the bottom row isn't. It's because the bottom row isn't connected. It's got to perfectly bridge the gap, and it does snap, by the way. It snaps so that it's perfectly bridging the gap. Now, this is our diagnostic tool here. It's got a whole bunch of wires. Each of these does a thing. Okay, you'll use most of these over the course of the semester, but do I have a live demo window open? It's saying live demo. But if I tried to just directly connect up X and Y and F into these chips, I'd have these wires sort of around there, and then I'd have to get the power and the ground wire in there. And so that would be most of the wiring. Now, can you even see the chip anymore? No. So if you make a mistake, you have almost no chance of debugging it. And most times you will not be getting it right the first time. So what we do instead is we keep the board, the analog discovery, off to the side. and we connect everything up like over here, off to the side, and we run wires from the chip over here. So when it comes time to, we can just rip the whole analog discovery board off, and all of our wiring stays the same. Okay, we don't have to go back and try to figure out, okay, this is third pin up from the top, and I feel like I'm on one of those infomercials where they open the doors and just, oh God. Okay, so what I wanted to show you though, before we get too much farther into wiring, is a few examples of wiring. Let me add this in here. Add in a window capture photos. Oh. Ooh. That's not good. Is it not gonna show these to me? Let me just do this then. Turn that off. Screen. Oh no, screen 1 doesn't work either. Why is this not? Yeah. No, go away. Oh, what I can do is I can go over here. Nope, I can't add photos to that either. I just wanted to show you a photo of good versus bad. Maybe I can do it like this. Maybe it won't be on the video. This is somebody's work. Okay. And this uses these pre-made jumper wires, and they're handy for a lot of things. This course is not one of those things. Just take these and promptly throw them in a junk bin somewhere. This is the same circuit, wired correct. Well, almost correctly. They did a weird thing off on the left, but yeah, trying to go from this to this, it's like it's night and day. One of these is easy to debug. The other is not. Okay, so I'll try to figure out how to get photos of those on there. But oh, actually, you can see it on my face. That'll be good. Okay. Back to Fritzing live demo. Okay, so here we are in Fritzing. Oh, I gotta move that and close it. Okay, we're back on Fritzing here. So the goal is before we wire the chip, we're gonna wire it virtually. That's why it's pre-visualization before we do it. So let's just turn off the live cam for a moment. Take this, like so. All right, so the first thing we're gonna do is we're gonna take into account that we don't wanna wire all of these components directly onto the board. So what I'm gonna do is I'm gonna just grab someplace off on the side of the board and connect them to the switches. I'm gonna do the same thing over here. Oop. This time I actually clicked on the dashed line. You notice how it became bold very fast? As soon as I let go of the mouse, it's put a wire in there. That's not what I want to do. So I'm going to just drag that wire in there. I'm also going to drag a wire from ground to ground and from power to power. And I've already gone ahead and bridged the power rails. So now both grounds are connected, both powers are connected. Also notice something that happened when I clicked on the power. It said, hey, this whole row should be electrically connected, which means you can drop a wire into any one of those yellow vertical dots. And if I do it on ground, same thing. So now I'm going to start wiring, and it doesn't really matter in what order you start because you're going to be moving wires as part of this pre-visualization process. So I'm going to just start with the inputs, and I notice right away that I need to connect up X there. And I also need to connect up X here. Now this is one way to do this. You can connect up from the source X to two different places. It does use up more wire though. A better solution is to daisy chain. So you go into this pin, then out of the next one over and off to the next. All right, now at this point, I'm getting a few wires on this board. It's becoming difficult for me to know which wire is which signal, which is where the next part of previs comes in. we want to be able to clearly delineate at a glance what signals go where. So I'm going to make use of the fact that we can colorize these wires. So I'm going to make X white. I'm just going to go over to this inspector view, and white is an option. I'm going to make Y yellow. All right, and I'm going to do that to every wire. Every single wire is going to have a color associated with it. I'm going to do the same thing, by the way, with power and ground. There's a convention that we use. Power is always red. Ground is always black. Same thing over here. Ground, black, power, red. It's a convention so that anybody can come to your circuit and say, oh, that's probably power. All right. So while we've got the wire red selected, I'm just going to go ahead and grab from red the power rail, going over to the power pin, and then I'll come over to ground and change that color to black. It is always a good idea anytime you need to hard connect something to power or ground to do it in short little jumps like that. Where's that life cam? Because a small little jumper wire, I'm going to plug this in backwards. A small little jumper wire isn't going to get in the way of any of your signal wires. And that's what you really want to avoid. You want to avoid having to separate out your signal wires from your actual power wires. Okay, so now the question is, am I even close to done yet? Well, if I want to know that, at the bottom of this screen, there's a little informational box here. It says 3 of 8 nets routed, 7 connections still to be routed. So it'll tell you how much you have left, and it'll also tell you if you're done. Okay, so I'm going to just keep going here. I'm going to make the output cyan. I like cyan. It's a delightful color. And so I just look at where does the output go. It only goes one place, right there. And I've still got to connect Y. So let's do Y now. Y should be yellow, so I'll make it yellow. Where else does Y have to go? It has to go all the way over here. Now, there is nothing stopping me from doing that. And then if you look on the live demo here, there's nothing saying I couldn't do this. Connect it right like that. Right like that. It's connected. It is electrically sound. From a prototyping standpoint, it is a problem because you have now locked your chip in place. And what was it you said? Smoke it, yes. If you smoke your chip, what does it mean to smoke someone in popular parlance? Oh, I wasn't thinking that popular parlance. Like Dirty Harry popular parlance. Shoot him. What happens when you get shot? Usually. It's fatal. So smoking a chip means that you have destroyed the chip. When you eventually take Dr. Rancor's 413 course, it's a CMOS VLSI design course. You're taking the grad version, both of you, actually. Oh, you're not? They teach you how these chips are built at the silicon level. They show you how they put the magic smoke in. And if you do bad things to the chip, the magic smoke escapes. And then the chip doesn't function anymore because these chips are obviously black magic. So you don't want to do that to your chips, but it does happen, okay? And if you do let the magic smoke out of your chip, you need to be able to remove this chip. I'm going to try and do it with this wire. So you got to carefully... You don't... Oh, damn. And then kind of carefully slide it out. And now you've got to get a new chip in and underneath it. So the rule of thumb is we never, ever will cover a chip. Okay, we just don't do it. If we do want to route a chip around like this, or across the chip, we just make a U. We just route around the chip. So as we continue on here, that covers that. What else do we need to do? Pin 3. Ooh, pin 3 needs to connect to a couple of places. It's neither X nor Y, so I'll give it another color. How about orange? Oop, not that one. That one's still supposed to be yellow. So we'll cut this wire. That's supposed to be orange. And it also needs to go over here. And again, same rules apply. We want to make sure that we don't cross things. We want things to look nice. What else do we need to do? That pin is connected. I'm just going along and clicking on everything and seeing if there's a wire to it. Here, we've got to make a connection. And I'll make this one pink. I like pink. Or purple. I'll do purple. All right, so now this is the real advantage of previs. We want this to go... Oh, let's not do that. It is possible to accidentally pick up the chip. You just want to make sure you place it back in the same place. It is possible now to put this purple wire in, but a bunch of problems have just appeared. Purple is now covering that yellow wire. It's crossing over the orange wire. Now, how many people have ever heard the phrase, measure twice, cut once? Okay, yeah. It's really easy to cut a piece of wood shorter. It's very hard to cut it longer. Think about that for a second. It's hard. Well, we're working inside of a computer. We've cut this orange wire. It is exactly this length. But there is nothing stopping us from making it longer. Get rid of some of these little wires, get in there. So now it's a little bit longer, and I can even move it further out. And again, any one of those wires or any one of those tie-in points that turns yellow is valid. So now I'm back to having no wires overlap. What's left to be connected here? Purple is connected. Ooh, that's got to be connected, so I'll put a wire there. Maybe make it green. Now the question is, am I done? How do I know if I'm done? Well, actually, the schematic capture package tells me routing completed. You've routed all of these wires. All done. So now it comes time to build this. So this is the next part of the demo. We've gone ahead. Remember, I've got to change my open board only. This was our steps. We've done a previs schematic. We've done a previs breadboard. Now we got to build the damn thing. Well, that requires its own set of skills. I swear this desk was clean this morning. And now it just looks like it did every other day. So when you come to lab the first time, let's go to Fritzing Live Demo. You get a selection of wires. You know, this will last you most of the semester. Maybe you'll need to get one color more than another. You got 5 colors of wire here: red, black, yellow, white, green, and blue. We don't have as many colors as we have in the computer, but we got to work with what we have. So this breadboard has already been prepared with some jumper wires. And what I'm going to do first is I'm going to make sure that I put the chip in. Okay. My pin 1 marker is there. Even if you can't see it, I promise it's there. Which means that pin 1 is in the upper left-hand corner. So I want ground to be close to the chip here and power to be close to the chip over there. And I'm going to go ahead and also bridge my power connections and my ground connections. I'm not using the correct color wire, but we'll get along reasonably well without that. So now I can begin wiring the chip. So I'm going to orient this the same way that the Fritzing diagram is oriented. And I got to make a bunch of connections. And I'm going to start with short connections. And we're only going to do about half of this, okay? And then I'm going to switch to one that I already made. But I want to show you a couple of techniques. So these are my wire strippers. These are what come with the kit. I also have, a little bit of a chintzy pair here. Most of the time, is there a pair of flush cutters on here? Somewhere, maybe in that drawer. It's just as a demonstration, it's not a big deal. At this point, I can strip a wire with just about anything. One of the people who is a senior now came into my 260 class one year, and he had a pair of 4-foot bolt cutters. I stripped the 22 gauge wire with 4-foot bolt cutters. He went away properly chastised. It doesn't really matter, but these kind right here, these are presettable. There is a little nut combination that will allow you to set the gauge of that little hole. Can everybody see that you can see light through that hole? That is specifically designed to be thinner than this insulation, but thicker than the wire. So now, I don't know what happened. Oh, I was working on a half-size breadboard before. Nope, this thing. Move this off to the side here. Okay, so there's my chip in there, and pin 1 is on my bottom left. Pin 14 is on the top right. So first thing I have to do is connect up the power. And there's a couple of things I want to call to your attention right off the bat. First is, how much insulation should you strip off of a wire? The answer is about 1/4 inch. This is much too much insulation. You just grab another breadboard here to show you why. This is a clear breadboard. It's extra fancy. There is only so much depth in a breadboard, and that is how far that wire will fit in. I don't know why it's insisting on not focusing. Focus, you. Anyway, so that's bad. You don't want to have extra wire poking out because it's going to cause a short. Some other wire will rub up against that. So the proper amount is about 1/4 inch. 1/4 inch looks like that. And when you insert it into one of these breadboard slots, it goes in just about to the insulation. Okay. So one might think that what you do is you get your 1/4 inch of insulation, you kind of size out the wire, then you cut it, and then you strip the other side. Well, depending on how long a wire you're going to strip, it gets kind of difficult. And it's a little difficult to show what I do here, but this is what, maybe I can do it here. Maybe I can do it here. To get this, I can't actually get a grip on this wire. It just comes right off my fingers. So what I do is I put a small joint into it. So now it's bent there. It's also bent on my fingers. And I turn it like a crank. At that point, if I just remove that, hopefully you can see the insulation has already been separated. Can you see this little silver there? If I wanted to, I could just take my fingers and remove that. Okay? But it just makes a nice clean cut on the insulation. If your pliers aren't properly adjusted, you'll bite into the wire a little bit, and it will cause a score in the wire. If you do that, it's going to have a tendency to snap right on that point. And that's not what you want. So make sure that your pliers are adjusted correctly. And when we come to the first lab next week, I'll come around and help people. At that point, though, it's just a matter of bending your leads into a U shape and then sticking them in a breadboard. So that works well for medium-sized wires. For short wires, though, specifically the kind that I want to go from, say, the ground rail to a single pin, it's actually easier. Let me get a black wire here. If I wanted to go from this ground rail to just that first pin, it's actually easier to strip off twice as much insulation, okay, and then give myself a shortcut that's going to tell me that amount of insulation, that's how much I want to bridge from one spot to another. Now, this doesn't help because I can't actually put this side into a breadboard. It doesn't fit because the insulation is too big. So what I do is I stick it in to the breadboard, and you see the insulation there, and I just take that insulation and I slide it right down. So now when I pull it out, look at how pretty that is. It's a joy, a beauty to behold forever. So now you take this, if you can get it off the table, and you bend it into a U shape. Get in there. And it bridges the bare minimum necessary. Okay? So that's the two kinds of wires you're generally going to be cutting. These mid-range wires and these short wires. The first one is always easy because you've got a whole handful that you can hold on to, so you can just sit there and strip this all day. You know, you've got plenty of grip. But if you're holding on with two little fingers, it doesn't really work. So what you want to do for a short wire is grip it, turn it into a bit of a Z crank, give it a couple of spins, and then that insulation will come right off. Okay. So as riveting as it was to watch me wire this thing one wire at a time last hour, anybody mind if I skip that and we just say, all right, I've put these together? The only wire that I do want to show you what I would normally do is how to size it to length. So I'm going to take a completely arbitrary wire. I want to say that I want to wire from here to there. All right. I want to wire from here to there. So obviously this is connected, but there's a lot of extra wire. So one of the things that you want to get good at is sizing your wire correctly. So you start with a piece longer than you need, one end stripped, and you stick it in the slot. Then what you're going to do is, put it nice and flat to the board. If you want to put a bend in it, just put your finger down, hold that, and it'll bend right around your finger. Then again, bend again. And then the last step, and this is more art than science, although you would think it would be a perfect mathematical equation. If you wanted to go into that hole where that green wire is, you should just cut it 1/4 of an inch past that. But for some reason, every time I've tried that today, I've come out much too long. But we'll see. All right, so now I have my wire. I've got to cut that. And I either could, change this bend, or I could just give it a little bit of a snip as it's already a U. It'll come off. So now I've got that U shape and both of those wires are pointing down. And then I fit it back into place. And that's still quite long. Yeah. But that's the basic idea, is you just want to make it nice and tight, which is what I've done on this sample right here. All right. So I've gone ahead and I've put some wires. Actually, that wire is a little long, but maybe something happened to it. I've put all the wires in, but I haven't actually put the chip in yet. And while I'm thinking of it, chips oftentimes, when they come fresh from the factory or straight from a warehouse or right from the stockroom, they actually aren't perfectly ready to go onto the breadboard. Oftentimes, the legs will be splayed out. Can you see how those go out at angles? All right, those don't naturally want to fit across that gap. They don't fit in well. Okay, you can see that it doesn't really want to see it. It'll sit halfway. So what you want to do to fix that is you just grip it on either end of the chip, and you're going to take it, and it naturally kind of rests back towards me because of the way the legs are splayed. So you just take it, give it a firm push, and a little roll motion. And now you can see one half of those legs is straight. And you give a little roll motion on the other side, just a little. Yep. Now they are both parallel, which is much easier to fit in. So now I'm going to stick this chip in. And actually, I won't stick it in there first. I want to stick it in here first because I want to show you how it'll sit naturally. If it is, focus, Focus. No cams. The camera was behaving much better during the first hour. All right, that's better. So you can actually see that the legs themselves do taper down. When you actually seat this correctly and just give a firm push on both sides of the chip, it just pops in that much. It'll just slide in. You shouldn't have to push forcefully. Very little force required to actually put this in. When it comes time to take the chip out, in your lab kit, you will have a small screwdriver. What you want to do is come in from one side, gently pry up just a little. Okay, you can see that it's only come out a little bit. Can you see that? That it's a little bit higher on the this side here. And you're then going to come in from the other side and do the same thing. Because if you do this wrong, for example, if you just take it and try to yank it out from one side, I think you can already see what's starting to happen. The back legs are still fully engaged, and the front legs are almost out. That means that if you've got a wire that's fully engaged in this, and then you start to bend it like this, what's going to happen to the legs? They're going to end up with a sharp bend in them. And that's bad because then they tend to break. They're very fragile. So you kind of want to do a little seesaw action until it comes out. Okay? Very gentle with chips. All right. So now I've got this guy built. I've wired him. It's time to test him. Because it's one thing to build a circuit. It's another thing to build a circuit that does what you want it to do. All right. So to do that, I need this tool right here. This is the digital and analog discovery. It is a Swiss Army tool of digital electronics. I love this thing. This is what I said was optional equipment on the syllabus. If you are a computer engineer, you should pick it up. You're going to use it in 260, 263, 368, 388, 457, 458. So it's totally worth it. And you can also take it out and use it in industry. It's perfectly serviceable in industry. What I want to call your attention to is this wire squid. Why do you refuse to focus? Okay. Okay. Nobody breathe. We've gotten it to focus. All right. This, everybody look in front of you. There should be a rainbow cable with a little squid on the end of it. Okay. It's the same squid, same markings, just an extension cable. It's split up into two halves. On the right half, you have these numbers 0 through 15. Those are your digital I/O pins. Digital I/O means they can read or write digital signals. They're I/O, they're input or output. So you can use them to read in digital values or to send out digital values. On the leftmost side, we have an oscilloscope, 2 channels. It's relatively low bandwidth, but if we really need high bandwidth, we do have a 100 megahertz one on the scope. But this is a nice 2-channel differential scope. Every one of these down arrows, which I think lasered into those, it just says V. Those are your grounds, and they do follow that convention of the black wires are ground. The next row over is V plus and V minus. There is a red and a white wire. Red is positive 5 volts. White is negative 5 volts, and I'll show you those power supplies in a second. What else do we have? Yellow we don't usually use. This is an analog waveform generator. So this morning I showed you a sine wave. This yellow wire can generate a real sine wave, a continuous sine wave. Yeah, it can generate a real sine wave. We'll just go with that. Now, the remainder of these pins, okay, first off, I want to call to your attention that the color scheme is always pink, green, purple, brown. So 0 through 3 are pink, green, purple, brown. 0, 1, 2, 3. 4, 5, 6, 7 is also pink, green, purple, brown. When you get to the lower set, if I can get just the lower ones here. All right, get those out of the way. You look at the lower set, they are also pink, green, purple, brown. Pink, green, purple, brown. But they have a little white stripe on them. So see, it's brown on top, white stripe on bottom. It's designed to help you easily suss out what you've got connected to things. So you've got 16 of these total. Today, we're only going to be using 3. So one of the things that is part of our lab, obviously these are sockets. Wires go into these. And one of the things you can do if you want is you can stick a wire into one side and then stick that wire into your board. Perfectly reasonable. But we also have double length headers. These are headers. One side sticks into the breadboard and the other side sticks onto your probe. So what I've done on this breadboard, okay, is over here for power and ground, I put 2 of those little guys in. Over here on the output, I put a zillion of them because these are breakable. You can take these and snap them into any length you want. But if you don't have to, just leave them together. Because the nice thing is if you are doing this with your own stuff, you might set up a particular order. It might need to go brown, green, purple. Well, then you can just pull the whole unit out and it'll stay brown, green, purple. It's stuck together. So that's just maybe don't snap them into a million single ones. All right, so here's how we're going to hook this up. First thing I'm going to do is I'm going to open the waveform software and figure out how to get it. External demo. Okay. So the waveform software, let's close it all up here. Can you open up? All right, when you first connect, nothing is open. It just has a welcome screen. Everybody can see that, right? It just has a welcome screen. All along the left side are a bunch of different tools. This one device can be an oscilloscope, a waveform generator, a power supply, a voltmeter, a logic analyzer, a pattern generator, a network analyzer, and spectrum analyzer for low-ish frequencies. So the first thing I'm going to do is I'm going to look at the power supply. I want my power supply to be a 5-volt power supply, although it can do various other voltages. By default, the negative supply is listed as ready. Save yourself a little bit of hassle. You never are going to use the negative supply in this course, so just turn it off. Now, there is still no power on going to this red wire. That red wire doesn't have any power on it until I turn the master enable on. Now, when I do turn the master enable on, there's a little icon in the top corner that says it's a red light, just like, you know, it's on for recording or it's functioning. When it's a play symbol, that means it's ready to go. So you hit play, it says it's running. When you hit the running, it stops it. Okay, so to hook up the power, I'm going to take a ground connection and a power connection. These 2 wires here, ground and power, red and black. And I'm going to hook them up. I'm going to try really hard to get the polarity correct, because otherwise you tend to let the magic smoke out. All right, so now I've got power and ground hooked up. Then I'm going to hook up my inputs. And I can use any any of these 16. But for my sanity, I'm going to start at 0 and work my way up. Okay? So I'm going to use 0 and 1 for my inputs. Now, where do my inputs go? Well, remember, I had a long wire on my previs that went off to the side. So all I got to do is make sure that they are connected in. So there it is, my white wire for X, my yellow wire for Y. Those are connected. And the last thing I want to look at is my output. So again, it's pink, green, purple, brown. So I'm going to take my purple wire here and hook him up to the output wire. Now, with this setup, let's get a high level view of this. All of my circuitry, all the stuff I wired up, is totally separate from this test apparatus. Which means if I have to, cut and run, I can just rip this cable right out, and all of this stays safe. Okay? And that's what you want to do while you're wiring up. So now let's get into the software that runs this tool. We talked about the power supply. All right. And one of the things I want to really stress is never make any changes either with the tool or on the circuit itself with the power on. Before you do anything, turn the power off. Why should you do that? Because if you accidentally, while you're unplugging this wire, touch it to another wire, you've created an electrical short. Shorts are never good. You don't want those. You let the magic smoke out. So always turn the power off. Okay, so we have 2 inputs. Now, we started this, remember, our workflow for open board was starting at a logical schematic. There's a whole bunch of other things that happen before we get to a logical schematic. All right, one of those things is the desired behavior. Now, this circuit has 2 inputs and 1 output. Now, how many different input combinations can we have if this is binary inputs? Each input can either be a 0 or a 1. What's one possible input combination? 0, 0. I could put 0 on X and 0 on Y. What else could I do? 0, 1. I could put a 0 on X and a 1 on Y. What's another combination? 1, 0. I could put a 1 on X and a 0 on Y. What's another combination? 1, 1. I could put 1 on X, 1 on Y. What's another combination? Huh? No, you could, that's actually a valid point. You could leave them disconnected, which would be bad. On the list of common ECE260 problems is leaving an input unconnected. We'll get into why that is in class a little later, but yes, thank you, smart Alec. Leave it disconnected. Well, that's actually all of them. And all we just did there, I don't know if you noticed, was we counted in binary. 0, 0, 0, 1, 1, 0, 1, 1. And the analog discovery lets us do that. So let's go back to external demo, turn on waveforms. And it lets us do that with a tool called the pattern generator. It's got the stuff from last time. When you start the pattern generator, it's a blank slate. Now, remember what we had set up was pink and green were our inputs, purple was our output. So we want to stimulate the inputs. Pink and green are input 0 and input 1, DIO 0, DIO 1. So I'm going to add stuff to this pattern generator. Now, since I want to treat pink and green together, their inputs together, it's called a bus. When you have multiple wires together, it's called a bus. When you have just a single wire, it's called a signal. So pink and green, they would be a bus. Purple would be a signal. So I'm going to add a bus in. I can give it a descriptive name like input. And what I'm going to do is I'm just going to select 0 and 1. Depending on how you choose these, if you just click, it will only select 1. If you click on one thing, hold Shift, and click on another, it'll select everything in between that. If you click on one and then hold Control and click on another, it'll only select those things. So for me, I just need DIO0 and DIO1. I then hit the plus symbol. Super important to hit plus. That moves it over to the right side of the window. You can't see any of this. Thanks for telling me. You're the best, guys. You see that now? All right. So let's go back and do it again. So if you hold Control and touch other units, you select only those. If you click on one of these, hold Shift, and somewhere else, it'll select all of those between. Okay. And if you just click on one, it only selects one. So I'm going to grab both 0 and 1. Those are the two inputs. I add them to the right side. And for now, I'm just going to have them be displayed as binary numbers. You could have it displayed as decimal or hexadecimal. Okay. And say add. Now we can go back to this here. So what it's done is create this bus. And what we want to do is we want to change its type. We want it to count in a binary sequence because that handles all the different combinations. So I'm just going to select binary counter. And I apparently didn't select decimal correctly. Or didn't select binary. There we go. So there it is, binary. Binary 00, 01, 10, 11. And it's going to repeat that sequence over and over and over again. So down at the bottom, get my head out of the way here, it's going to be 0, 0 for 1 millisecond, which means it's changing its value 1,000 times a second. Can you guys keep track of 1,000 changes per second? No. So we need something that can, and that's another tool built into the analog discovery. It's called a logic analyzer. Logic analyzers look at lots of digital inputs very quickly. So it may seem redundant. We had a pattern generator. We added a bus with 0 and 1 on it. When I go to the logic analyzer, I'm going to add a bus called the same thing with the same items, 0 and 1. And let's reset this here and add it in. Exactly the same. That is because we want to look at what we are providing as input. So if I turn the pattern generator on and I turn the logic analyzer on, you can see that it's running. Okay, there's a time base along the top here. It's triggering, I don't know, 20 times a second visibly, doing 20 waveforms a second. But can you really see what's going on here? Does it seem like it's imparting any useful information? No. That's because it's just triggering as fast as it can. It's just showing you whatever's on screen at that time. What we can do, however, is synchronize it. It would be nice if we could get it to show 0 right in the center. Every time we show a 0, that's what we want to trigger. So these items right here, they're right now called X's, or they're shown as X's, meaning don't cares. If you click on one of them, you can say, hey, only trigger when this most significant bit goes from a 1 to a 0, which is called a falling edge. And all of a sudden, just like that, time 0, right there, is where this guy has a falling edge. Now, if I want to click and drag around on that, okay, I can. And now you can see 0, 1, 2, 3 are shown. Now, it looks static. It looks like it's not changing. But if you look at the time base, it's actually still triggering a zillion times a second. Okay? So it's still running over and over and over again. So the last thing we need to do now, remember, we've already hooked it up. We've already hooked it up on here. So we're actually providing inputs to this chip. So we should be seeing something on this output. So let's add one more signal here. Add a single signal, DIO2, add it in. and we see a big black nothing. Big lot of nothing. And this is a fairly common occurrence. Does anybody see what might be wrong? George, why am I not getting any output? That's what the output is, yes?
Well, it's also because you didn't turn on the supply. That's
absolutely right. I didn't turn on the supply. You only got that by the skin of your teeth, George. You got to turn the thing on. Turn it on. Go back. Now I've got some output here, and I can zoom in. I can see many, cycles of this output waveform. And I see 0, 1, 2, 3. Those are my inputs, and this is my output. So the question is this correct? You would know that from the problem specification. I'm going to tell you it is, okay? But if it wasn't, and it wasn't earlier today, let's just quickly, I'm going to quickly break it, okay? And I'm going to do all the wrong things. I'm going to not turn the power off. I'm going to move everything around. It's going to be terrible. All right, now I'm not seeing the right output. Did you see what changed? It used to be 2 low pulses and 2 high pulses. Now it's 1 low pulse, 3 high pulses, which is not what we were trying to do at all. The reason for that is the most common problem with all ECE260 wirings. What's the problem with that? To see anything that looks out of place? What's wrong? Yeah, not having a ground connection is a great way to get really weird results. Like really weird. So the first thing I'm going to do when you say, Professor, my circuit doesn't work, is I'm going to check your ground. If I plug the ground back in, all right, watch as I do it live, taking my life in my hands. Oh, we're back to working again. Now, not all debugging is going to be this simple. Coming back here. If this is your circuit, it is possible that you might not get the correct output here. It will be wrong. There are only 3 causes for this thing to be wrong. Well, 3 things that could be wrong. 1, the input on pin 12 could be wrong. The input on pin 13 could be wrong. That's 2. Or the chip has a problem. That could be a ground problem. It could be that this particular chip is bad. Now I have up here a chip tester, okay? And I could take this chip out after turning the power off. Go back to waveforms here for a second. Turn the power supply off. All right. And I'm going to, what's showing up here? Okay. Carefully take the chip out. And I stick it in my little chip tester. Oh. Can you see that guy? And I say, ooh, not found. Ha! All right. It's correctly identified that it is a 74LS00 and that it's a good chip. Okay. 132 is another chip it could be. It's the same pin out. It's a NAND gate. It's just a different thing. So, but the 7400 is what I want. I've got a couple of these testers lying around. I will bring them around to you and test your chip for you if you want. 99 times out of 100, it's not the chip. Okay? So, if it's not the chip, it's got to be one of the inputs. So here's what you do to solve this, okay? You've got your board, you've got your chip installed in the board. If the output on pin 11 is wrong, then I'm going to look at 12 and 13. So I'm going to just grab, I've got plenty of wires here, so I'll grab these 2. And with a little testing wire, I'll come over here and I'll look at pin 12, 14, 13, 12. And I'll look at it on the logic analyzer. Now, then either 12 will be correct, it'll have the correct waveform shown, or it'll be wrong. All right. Now, if it's correct, then I would move on to pin 13, right? And I'd look at pin 13. And either it's correct or it's wrong. Now, if they're both correct, probably there's a problem with circuit 4, gate 4. But if one of them is wrong, that means one of 4 things is wrong. Either, for example, if 12 was wrong, either 6 is wrong, 4 is wrong, 5 is wrong, or gate 2 is wrong. Now, at this point, we've probably already tested the chip, so it's probably not gate 2. So what I'm going to do now is, instead of being on pin 12, I'm going to go and look at pin 6. Now, there are 2 options. Either 6 is correct or 6 is wrong. Now, if 6 is wrong, or 6 is correct and 12 is wrong, that is diagnostically very important because they're supposed to be the same. So why would they be different? Because you wired it wrong. Because the wire is not connected to what you think it's connected. So you check, but what you've done though through this process is you've narrowed it down to, oh, I should look at this wire. And you go to your fritzing schematic and you say, oh, I need to look at that green wire. And so you look at it and you say, oh, it's off by 1. Plug it in, redo the test. So the testing itself is iterative, all the way back to build the damn thing again. That's one option. However, if 6 and 12 are both wrong, go back to my open board. If 6 and 12 are both wrong, then you repeat the process. You look at 4 and 5. Now, 4 is really easy to check. 4 should be equal to whatever x is. If it's not, it's a wiring error. If it's 5, if 5 is wrong, well, then you look at 3. Now, if 3 and 5 are different, wiring error. If they're the same, well, then you look at 1 and 2. You trace it back. But notice, I never looked at those pins because there was nothing wrong with those pins. So you've got to narrow down your focus when you're debugging. And this is an acquired skill. You only learn this by doing over and over. But it is not a guess and check. There is a systematic approach to debugging that you should take. Well, I have just about talked myself hoarse. Did I forget anything? Okay. So, reminder, there are reading assignments on the syllabus. The labs are already listed in your syllabus. They're in the back of your book, chapter 9. So check those out. Start working on some fritzing schematics because it's going to save you time in the long run. And we made it through the whole thing.